Okay, it's flashing, so I think it's recording. And I can check. Yes, it looks like it is recording. Okay, maybe this time I'll successfully record. Okay, sorry for that slight delay in getting started. Let's begin. Today what I'm going to do is continue with our discussion of the two-body problem. So just to remind you of how we began discussing the two-body problem last time. So in the two-body problem, we consider a system of two masses which interact via a central force potential, via some central force which points between the two objects. So the Lagrangian will be, let me just zoom in a bit, will be 1/2 R1 dot squared times M1 plus 1/2 M2 R2 dot squared minus a central force term, which comes from a potential that is a function only of the distance between the 2 points. So this is a system with 6 degrees of freedom, 3 for each of the positions of the objects. And we simplified the equations of motion of this system using Noether's theorem. So Noether's theorem implies that for any continuous symmetry, which is to say, for any transformation of the dynamical variables that I use to describe the system, say Qi to big Qi, which will depend on S as well as on time and the little Qi's, I can define the Noether current, or the Noether charge, I, which is the sum over all of the degrees of freedom of the momentum, Pi, conjugate to a given degree of freedom, times dq I by ds. And this will be a constant of motion. Provided this is a symmetry that leaves the Lagrangian invariant. So I should mention that this formula for the Noether charge, as I emphasized last class, is only true for those symmetries that leave the Lagrangian invariant. And on your problem set, you will consider how to extend this to symmetries which leave the equations of motion invariant, but not necessarily the Lagrangian. But for our purposes today, this setup is sufficient. So for example, last time I noticed that there are 3 obvious symmetries of the two-body problem, where I take R1 to R1 plus a constant vector A, as well as R2 to R2 plus the same constant vector. So this is a set of 3 continuous symmetries, one for each component of the vector A. So, for example, if I compute the conserved quantity associated to A1, the first component of A, then that is the total momentum pointing in the x direction. Likewise, the conserved quantity associated with the second and third components of A are the total linear momentum in the y and z directions. So just to be a little more explicit, if I let P1 be the momentum associated with R1, which is m R1 dot, and likewise P2 is the momentum associated with R2, sorry, there's some dots there, I forgot, which is M2 R2 dot, then the invariance of the Lagrangian under shifts by this constant vector A implies that the sum of P1 and P2, which is the total momentum of the system, is a constant. for any solution of the equations of motion. Because of that, we decided that it would be useful to separate the system into a center of mass and relative position variables. So rather than using the variables R1 and R2, we decided to use the center of mass variable, which is M1 R1 plus M2 R2, as well as the relative variable R2 minus R1. So this is just a change of variables. Instead of using the 6 quantities R1 vector and R2 vector, I will use the 6 quantities describing the center of mass and relative positions of these two objects. And in terms of these new degrees of freedom, the Lagrangian is equal to 1/2 M1 plus M2 times the derivative of the center of mass position. So that just looks like the Lagrangian for a free particle in 3 dimensions with center of mass position RCM, plus a term depending on the relative position, which was 1/2 mu r dot squared minus v, which will be some function of the length of the vector r. Here, mu was the reduced mass, m1 times m2 over m1 plus m2, and it's just a straightforward algebraic exercise to check that this Lagrangian is identical to the Lagrangian that I wrote down above for the two-body problem. And the advantage of this is that we can now solve completely for the center of mass motion. So because the center of mass momentum is constant, the center of mass position is just a constant vector times t plus another constant vector, just as it would be for a free particle which is moving with no external forces acting on it. And we are left with, so we can just, if we like, forget about the center of mass motion. That's just some free particle. And we are left with a system with 3 degrees of freedom, described by the Lagrangian 1/2 m mu r dot squared minus v of r. So this was an example of the use of Noether's theorem to reduce the number of degrees of freedom from 6 down to 3. So we've solved for 3 of the degrees of freedom, and we have 3 remaining. Question? Did I make a mistake? Yes? Oh, I'm sorry. Thank you. That's what happens when I try and ad-lib. Yes. Thank you for that. Any other mistakes? Any questions on this? I should emphasize that if I were considering a system of 27 masses interacting via some potential, instead of 2 masses interacting via some potential, then as long as this potential, as a function of those 27 positions, only depended on the relative distances between those objects, then I could do exactly the same set of manipulations. I could see that the total momentum was conserved, and I could reduce it from 27 times 3 degrees of freedom to 26 times 3 degrees of freedom. So just because I've only worked it out explicitly in the case of a two-body system where I go from 6 to 3, exactly the same set of manipulations will work in general. There may even be, hopefully I assign a problem at some point involving the 3-body problem or something like that, where you can see this explicitly. Is that clear to everyone? So you all understand how if you had 27 objects, you could use the Noether's theorem to eliminate 3 of the center of mass degrees of freedom. Hopefully that is, if it's not obvious how you would do it, then I encourage you to work it out explicitly. Maybe not 27, that might take a long time. Try 3. Then try n, where n is a number. Okay, so that was half of what we did yesterday. The other slightly more sophisticated use of Noether's theorem involved the conservation of angular momentum. So we noticed that this action is rotationally invariant because it only depends on the length of the velocity vector r dot and the length of the vector r. So it does not depend on a rotation of the coordinate system. And although I could, if I wanted to, and I will later in this class, write down very explicit formulas for rotation matrices, all that is needed in this case is the fact that under an infinitesimal rotation, by an angle epsilon about the axis alpha takes the position vector r to r plus epsilon alpha cross r, or using index notation, it takes the vector r, which is now written as a set of three quantities, ri, where I is 1, 2, or 3, to ri plus epsilon times the epsilon symbol, I, j, k, which is equal to plus or minus 1 if I, j, and k are an even or odd permutation of 1, 2, and 3, respectively, and is equal to 0 if any two of the indices I, j, and k are equal, times alpha j rk summed over j and k running from 1 up to 3. So this is just a way of writing the cross product using index notation. So, you can see from this formula that the variation of r under a rotation, so this is the quantity that I've indicated here, is the variation of r under an infinitesimal rotation, which is the thing that in the definition of Noether's theorem I called dq by ds. So here qi would be the three components ri, where r runs from 1 up to 3, and s would be the parameter epsilon. So dqi by ds would be dri by d epsilon, which is the sum over j and k, alpha j rk, epsilon I, j, k. Again, where I sum j and k from 1 up to 3. So if I plug in for the definition of the Noether charge, I just take this and I sum over I, pi times this guy that I have written here. So I get a sum over I, j, and k of pi alpha j rk epsilon I, j, k. So for a rotation about the axis alpha, the conserved quantity is alpha j pi rk contracted times epsilon I, j, k summed over I, j, and k running from 1 up to 3. Or using vector notation, that would be alpha dotted into the vector L, where L is the vector R cross P, or in index notation, Li would be equal to epsilon I, j, k, rj, pk. So for a rotation around the axis pointing in the alpha direction, where alpha is some unit vector, the conserved quantity is alpha dotted into the angular momentum vector L. So this is going to be a constant for any rotation, So for any vector alpha, and so what that means is that the three quantities L form a constant of motion for any solution to the equations of motion of the system. And of course, I don't even need to put quotes around it. This constant of motion is known as the angular momentum. I should make one important comment here, which I did mention last time, which is that this derivation that you see on the transparency up here really did not require the specific form of the Lagrangian. All I did is I noted that R transforms like a vector, so which is to say R transforms using this cross product formula, and then I just plugged in the definition of the Noether charge to write down the conserved angular momentum as R cross P. So the detailed form of the Lagrangian did not enter here. So this expression for the conserved angular momentum will be true in any theory which is rotationally invariant. For example, if I have 27 masses which interact via some central force potential, then I could reduce the system from 27 times 3 to 26 times 3 degrees of freedom using linear momentum conservation. And then I could get rid of additional degrees of freedom using angular momentum conservation. So is that clear? I also encourage you to try and work this out for yourselves. So perhaps I should write it down. So this formula did not depend on the details of the action, only on the fact that L was rotationally invariant. So if we wish to write down a slightly more explicit formula for L in terms of R and its derivatives rather than just in terms of R and P, then we need to know what the momentum P is. So the momentum P in this case for our specific action was dl by dr dot, which was mu times r dot, mu times the velocity. So for our problem, the angular momentum vector is mu times the cross product of the position and the velocity. So that is a somewhat more familiar looking formula for the angular momentum, which you probably saw in your previous mechanics classes. And in fact, it's quite easy to check that this is indeed a constant for a solution to the equations of motion. So that's what I would like to do next. Before I do so, are there any questions? Okay. So in order to check that this is a solution, or check that this is a constant of motion, let's look at our Lagrangian here. So we have 1/2 mu r dot squared minus v of r. So if we write down the Euler-Lagrange equations coming from this action, it's a little easier to write down in index notation. So let's let r, the vector r, be given by the three quantities ri, where I runs from 1 up to 3. Then the three equations of motion will be given by the variational derivatives of the action with respect to ri. So those three equations of motion, well, first we will have d by dt of the derivative of the kinetic term with respect to ri dot, where I is 1, 2, or 3. So that will be mu times ri dot. And then we have to subtract the derivative of the Lagrangian with respect to ri rather than ri dot. So you need to compute the derivative of the potential with respect to Ri. So if we just remember that this norm, the length of the vector r, is the square root of the sum over I of Ri squared, right? It's just the square root of R1 squared plus R2 squared plus R3 squared, or the square root of x squared plus y squared plus z squared. Then just using the chain rule, the derivative of v with respect to Ri will be equal to v prime times Ri over r. So Ri over r is just the derivative of this norm r with respect to Ri. Is that clear? So the equation of motion is mu Ri double dot plus v prime Ri over r is equal to 0. Or you could write this in vector notation if you like. It would just be, sorry, I probably should have put an upper index there. Otherwise I'll be very upset. In vector notation, of course, you could write this as mu times the acceleration vector plus v prime, the vector r over r, is equal to 0. Any questions on that? Okay. So what is the angular momentum in this index notation? The angular momentum vector has three components, which are given by mu times the sum over j and k of epsilon I, j, k, rj, rk dot. So that's just the cross product between r and r dot written using this index notation. So we can then compute the time derivative of Li. So what is that? Mu times the sum over j and k, epsilon I, j, k, times the time derivative of rj, rk dot. So that's rj dot, rk dot, plus rj, rk double dot. So that first term is going to be 0. This rj dot, rk dot term is going to be 0. Why is it going to be 0? Well, the epsilon symbol changes sign if I switch j and k. Because if I switch j and k, then if ijk was an even permutation of 1, 2, 3, it becomes an odd permutation and vice versa. So that means that this r dot j, r dot k term has to vanish. So you all actually know that fact. This is the statement that the cross product of a vector with itself is equal to 0. Okay? In vector notation, this would be L vector dot would be equal to mu times the derivative of r cross r dot, which would be r dot cross r dot. That would be the first term, plus r cross r double dot. So that first term obviously vanishes. And now, if we use the second equation of motion, for the second term we use the equation of motion. So in vector language, the equation of motion says that r vector double dot is equal to minus v prime over mu r vector over r. So in vector notation, that means, well, what that means is that rk double dot is proportional to rk. So that this term is proportional to rj times rk and is equal to 0 by the equations of motion. Or in vector notation, I would say that L dot is mu times r cross minus v prime over mu r over the length of r, which is equal to 0 because the vector r across itself is equal to 0. So I haven't told you anything you don't already know, because I proved to you that Noether's theorem always gives you a quantity which is constant for a solution to the equations of motion. And so it had to work out this way. And so this was just a check that we had done everything correctly and applied Noether's theorem correctly to find a quantity which is a constant of motion. Any questions on that before I go on? Okay. So now we can use the angular momentum conservation to eliminate 2 more degrees of freedom and reduce our system from a system with 3 degrees of freedom down to a system with 1 degree of freedom. And as you have already learned, every system with 1 degree of freedom is exactly solvable. You just do some integral. Okay, so how do we go ahead and do that? Well, the angular momentum vector is the cross product of r and the momentum, or mu times the cross product of r and the velocity vector r dot. So if that's a constant, that means that the vector r will always lie in the plane which is perpendicular to the vector L. That's what the cross product means. R dotted by L is dotted into L is equal to 0. So that means that the vector r always lies in a plane. The conservation of angular momentum means that all of the motion will lie in a plane. And it's the plane that is perpendicular to the angular momentum vector. So let's just choose our coordinates so that the angular momentum vector points in the z direction. We can choose whatever coordinate system we like by rotational invariance. So let's just choose the z direction to be the direction which is the direction that the angular momentum vector points in. And Lz, the component of the angular momentum vector in this coordinate system, will just be some number which is a constant of motion. And so that means that the position vector will live only in the x and y directions. So I can use polar coordinates to describe the position vector in those coordinates. And it'll just be r, the length of the vector, times cosine phi or sine phi if I'm looking at the x or y coordinate, respectively. So let's go ahead and then compute the angular momentum vector. So the momentum vector is mu times the time derivative of the position. Both r and phi will be functions of t. So this will be the sum of 2 terms. The first is mu times the term where the derivative hits r, and then there will be a term where the derivative hits phi. So I can then go ahead and compute the angular momentum vector. It's just the cross product of those 2 vectors. And that will be the sum of 2 terms, because the momentum vector was the sum of 2 terms. Now the first term is where r vector is crossed with this vector right here, which points in the same direction as the r vector. So that's going to be 0. So we're only left with the cross product of r with that second term there, which will be r squared phi dot times the cross product of those 2 vectors. And now the cross product of those 2 vectors is just z hat. sorry, I left out a mu there. That may be why all of you guys are looking uncomfortable. So the cross product of those two vectors is z hat. Do you want to compute that? So compute the first component of the cross product. That's 0. The second component of the cross product, that's 0. The third component of the cross product is cosine squared plus sine squared, otherwise known as 1. Right? I mean, that's how you compute cross products. You sort of look at it and then you figure out the cross product. Right? Isn't that how they taught you to do it in your calculus class? Okay. Anyway, it had to work out like this because I chose the angular momentum vector to point in the z direction. So this was what I called LZ times z hat. So what that means is that whereas you might think that I have 2 degrees of freedom corresponding to the r and the phi coordinates as a function of time, in fact, I can solve for phi dot in terms of r. Just by looking at this equation for the angular momentum vector, it's LZ over mu times r squared. LZ being a constant of motion, it is the length of the angular momentum vector. So this allows us to completely determine the angular velocity as a function of the position. It's just a constant over the position, the distance r squared. So this will allow us to remove an additional degree of freedom and write the dynamics completely as a one-dimensional system. So that is what I'm going to do now. Before I do so, are there any questions on the manipulation that I just went through? No questions? Okay, let's finish up then. So, in order to finish up, what I would need to do now is write the equations of motion in these polar coordinates. So, how do I start? Well, we could start in spherical coordinates, where r is equal to the magnitude of the vector r times sine theta cosine phi sine theta sine phi and cosine theta. And then we can write the Lagrangian as a function of r, theta, and phi, as well as their time derivatives. Now, I believe I made you go through this exercise for the spherical pendulum in one of your earlier problem sets. Is that correct? So you might remember from that problem that when you write the kinetic term 1/2 mr dot squared in polar coordinates, you'll get 1/2 mu r dot times the sum of 3 terms, one of which involves the derivative of r squared, the length of the vector r squared, another term involving theta dot squared, and another term involving sine squared theta times phi dot squared. So this is essentially what you did in your first problem set when you studied the spherical pendulum. You probably had r fixed, so you didn't have an r dot squared term there, and you probably called it L instead of r, but it's exactly the same computation. So is that clear? And would you like me to do that explicitly? It's very easy to do. You just take this expression for the polar coordinates, you insert it into that lower expression, you start computing time derivatives, you square the vector, and then you cancel a bunch of sines and cosines against each other, and you get this lower expression that I've written. So we can then proceed to write the equations of motion for r dot, theta dot, and phi dot. Let me just write down the r dot equation of the r equation of motion. So the r equation of motion says that 0 is the time derivative of the Lagrangian with respect to r dot, which is mu r double dot, minus the derivative of the Lagrangian with respect to r. So now, oh, I'm sorry, there's a dot there that shouldn't be there. Is that what you guys were whispering? Yeah, okay. You shouldn't whisper, you should tell me when I make mistakes like that. So we subtract the derivative of the Lagrangian with respect to r, and we get mu times r times theta dot squared plus sine squared theta phi dot squared plus v prime as a function of r. Now, remember that we are using coordinates where L is proportional to z hat, so that the motion is completely confined to the plane where the z component of r is equal to 0, which in these polar coordinates means that the motion lies in the plane theta equals to pi over 2, because that's when cosine theta is equal to 0 and sine theta is equal to 1. So if we plug theta equals pi over 2 into this equation of motion for r, we get mu r double dot minus phi dot squared plus v prime is equal to 0. And now, I showed you earlier that the conservation of angular momentum allows us to solve for phi dot as a function of r. So if we plug that formula in here, I'm sorry, the tablet isn't quite big enough for you to see them both at the same time. So phi dot was equal to L over mu times r squared. Plugging that in here, we see that mu r double dot is equal to minus v prime plus phi dot squared, which is lz squared over mu squared r to the fourth. Yes. Did I make a mistake? Oh, I'm sorry. Mu r. Right. I'll never get the right answer that way. Mu times r cubed. See, this is what happens when I don't stare at my notes continuously. Any other mistakes? I don't think I made any other mistakes. Thank you. Okay. So, I should make a very important point here. So you'll notice that the way that I proceeded is I first wrote the action in polar coordinates, then I wrote the equations of motion in polar coordinates, and then I plugged in the constraints on phi and theta. I did not write the action in polar coordinates, plug in the constraints, and then compute the equations of motion. Those are two different things. And one of them is right and the other is wrong. So it is a famous mistake that many people make in studying mechanical systems, is that people plug in the constraints into the action and then derive the equations of motion from this constrained action, rather than computing the equations of motion and plugging in the constraints only at the level of the equations of motion. And so I encourage you to convince yourself that we need to impose the constraint theta equals pi over 2 and phi dot is L over mu r squared only in the equations of motion, not in the Lagrangian. So let's imagine that I had done the other thing. Let's imagine that I had plugged in the constraint where theta is equal to pi over 2 and phi dot is something times 1 over r squared directly into the Lagrangian. Then what would have happened? This term would have been equal to 0, and this term would have been equal to 1, and that term would have been something over r squared. And so it would have looked like, it would have looked like an action that's a function of r and r dot, and I would have computed its equations of motion. But if you go through it, you'll find out that the equations of motion you would get are different from these equations here. You would find that you would have made a sign mistake. You would have gotten this sign here wrong. So I mention this because this is an error that many people make, and I want to warn you against it. So if you think about it, you can understand why it is that you're not allowed to plug in these constraints at the level of the action, but only at the level of the equations of motion. So why is that? So the constraint that phi dot is L over mu r squared comes from Noether's theorem. It's a conserved quantity, which is a constant of motion only on a solution to the equations of motion. So phi dot, it goes like 1 over r squared only for a solution to the equations of motion. But the equations of motion are found by varying the action. And when you vary the action, you consider small perturbations away from solutions to the equations of motion. So you shouldn't assume that you have a solution to the equations of motion when you're studying things which are not quite solutions to the equations of motion, which are what you use when you use the variational principle to derive the equations of motion. So it's a very common mistake I see that people plug in expressions for conserved quantities, conservation laws, into the action, and then treat that as a new action from which you derive the equations of motion. Sometimes, if you're lucky, you'll still get the right answer, but more often you'll end up getting the wrong answer. So I recommend working through that very carefully in this case, just to see exactly why you'll go wrong. Any questions before I continue? I think there's a whole section in the book devoted to making sure that you don't make this mistake. So I recommend you read that it's one of these little boxes on the side of the book. I recommend you read through that carefully. It's a mistake that, you put this problem on an exam and you're guaranteed that half of the people are going to get it wrong. So I'm warning you right now. Don't get it wrong. Okay. So having given you this warning, let me now spend a minute just talking about this equation of motion right here. So this equation of motion, you can tell it's important because I've already drawn 3 arrows around it. And I'll also draw a box around it. Why is that an important result? Well, the remarkable thing is that this equation, it looks just like the dynamics of a particle moving in one dimension with position r. And in particular, it looks just like I could write this equation as mu r double dot is equal to minus v prime effective, where v prime effective is some sort of new potential called the effective potential, which is the potential that would be felt by this one-dimensional system. So this is not to say, of course, that two-body motion is the same as a motion of a particle moving in one dimension, but that the equations of motion, once you use the conservation of angular momentum, are the same as the equations of motion of a one-dimensional system. So that we can now use all of the tricks that we have developed for dealing with one-dimensional systems to deal with the two-body problem. And in particular, you will see that we will use all of the tricks that we developed for one-dimensional systems to study the two-body problem. And here, V effective I can read off from the equation with 3 arrows and a box around it. It's V plus L squared over 2 mu R squared. There's a plus sign and a 1/2 because this equation up here is the derivative of V. So you take the derivative and you get a minus 2 coming from the 1 over R squared. Okay. So at this point, I could stop lecturing because you now know everything you need to solve completely the two-body problem. You just use the exact same techniques that we use to study the two-body problem, the motion of a one-dimensional system. So, for example, there is a conserved energy which is equal to 1/2 mu R dot squared plus V effective. And this energy is a constant of motion. And then we could proceed to solve the equations of motion by writing down an integral. And so the time that it would take for the distance between the two objects to change from R0 to R1 would be given by the integral from R0 to R1 dr over the square root of 2 times E minus V effective. I should note here that there are two constants of motion that appear in this formula. There is E, which is a constant of motion, what I called E effective there, as well as L, which is the conserved angular momentum. So it's probably worth mentioning that this effective potential is itself a function of the angular momentum. So it's only when I use the fact that angular momentum is conserved that I can write down an expression for the effective potential in terms of L. And for orbits or trajectories with different angular momenta, the form of the effective potential will look different. So what I would like to do now is I would like to explore in some considerable detail one special case of this, which is the case of gravitational attraction. But before I do so, are there any questions on this? You probably saw the effective potential in your previous mechanics class. Probably didn't understand it very well. Not as well as you do now. No questions? I hear whispering. Maybe I'm just hearing things. Okay. So let's consider the case where I have two objects which are interacting gravitationally. Such as the Earth and the Sun. So in that case, the potential is minus Newton's constant m1, m2 over r, and the effective potential, well, there's minus gm1, m2 over r. I'll write that as minus k over r, where I let k be g m1, m2, plus beta over r squared, where beta is L squared over 2 mu. I'll get tired of writing down my constants all over the place. So I'll just call them K and beta. So what does the effective potential look like as a function of R? Well, if I graph the effective potential as a function of R, at very small values of R, the 1 over R squared term will be big. So it'll be large and positive. It'll decrease as a function of R till you get to some point where those two terms will be of the same size. at which point the potential will turn over and approach zero at large distances. Note that it approaches zero at large r from below, because at large r, this effective potential is minus k over r. So it goes like 1 over r at large distances with a negative coefficient. So now just by staring at this and thinking of this as a one-dimensional potential, you can immediately understand what the solutions to the equations of motion look like. There is a stable minimum at a particular value of r and a particular value of v, which is negative. There are going to be bound solutions when the energy is less than 0 but greater than v min. So those will be the solutions where r oscillates around v min in some way, which will correspond to bound orbits. For the circular orbit, where E is equal to v min, of course r will be a constant, so we would have a circular stable orbit. If you wish to study small fluctuations around that stable orbit, you could do so. They will be described by a simple harmonic oscillator, just like everything is. In fact, we won't even need to work in a perturbation expansion because we can actually solve the equations of motion exactly, as I will do in a few minutes. But you can also see, just by looking at the functional form of the effective potential, that there will be some sort of unstable orbits or unbound orbits where the energy is greater than 0. So for this unbound motion, an object will have infinite radius at t goes to minus infinity and plus infinity, and it'll come into some minimum distance. So if this is the value of E, then there'll be some sort of turning point at the trajectory where the value of R is minimized, and at future and late times, the objects will be very far apart. And finally, when E is equal to 0, you have some sort of marginal case where the motion is unbound, but sort of only barely. So this will be some sort of special case, much like, in fact, if you look at the phase diagram, it'll be a separatrix, just like we had for the pendulum. So I won't write it out explicitly, but I encourage you to make a graph of the phase diagram of this and get used to it. And you'll see that there are stable orbits, unstable orbits, a separatrix separating the two. That's a fun exercise. I recommend you do it. It's probably in the book. I'm not sure. Okay. Any questions before I continue? So it turns out that the equations of motion can be solved exactly in this case. So let me just write down the equations of motion so I don't forget them. So mu times r double dot was minus v prime, where v prime was this effective potential. So you'll have plus k over r squared minus beta over 2 r cubed. I hope I got that right. If I didn't get this right, I'll never be able to get the right answer. In order to, so you can see I put this up at the top to give myself a lot of room. So the computation that I'm about to give you is a little bit technical. It involves a famous trick, which I think is originally due to Isaac Newton, which is it's a very famous trick for solving this equation. And it shows up again and again in physics. So it's useful to understand explicitly. So if I just handed you this differential equation, was there a comment? Okay. If I just handed you this differential equation and asked you to solve it, you probably would not be very happy with me because the solution is not entirely obvious the way that I've written it. But in fact, there's a set of manipulations that I can do which will make this differential equation turn into something that I have already bored you to death talking about. So in particular, the trick that I would like to use is I would like to, instead of thinking of t as the dependent variable, I would like to think of phi as the dependent variable. So rather than thinking of r of t, I would like to think of r as a function of phi. So why can I do that? Well, phi dot is L over mu r squared. That's strictly positive. So that means that phi is a monotonically increasing function of t. So I could use whichever one I like as the dependent variable in this differential equation. And so let me just tell you that life is much simpler if we use phi. This is also nice because if I know r of phi, then I know the graph, then it's very easy to understand what the graph of the orbit looks like in the xy plane. Because I know the distance, the polar coordinate r as a function of phi. It gives me the graph of the orbit in polar coordinates. So, in order to write this differential equation using phi as the dependent variable, well, I just need to use the chain rule a bunch. So, r dot will be equal to, so that's dr by dt, which is equal to d phi by dt times dr by d phi, or phi dot times r prime. So here, dot will denote d by dt, and prime will denote d by d phi. So plugging in my formula for phi dot, I see that r dot is L over mu r squared times r prime. So if I wanted to go ahead and compute r double dot, then I need to take the time derivative of this guy again. So that's phi dot times the phi derivative of r prime of phi dot times r prime. So L over mu r squared r prime prime. So that's L over mu r squared times L over mu r double prime over r squared minus r prime squared. So there's an L over mu r prime squared over 2 r cubed. So that is equal to L over mu squared times one over r squared, r double prime over r squared minus 2 r prime squared over r cubed. Okay, that was trick number 1. Now here's trick number 2. There's always a trick number 2. Trick number 2 is that rather than consider r as the variable, the independent variable, let's consider the following. Let's let u be 1 over r. Okay? So that means that r is 1 over u. R prime is minus u prime over u squared. And r double prime is the sum of 2 terms, minus u double prime over u squared plus u prime squared times 2 over u cubed. So let's go ahead and take these two guys and plug them into here. Everyone with me so far? So R double prime is L over mu squared times 1 over r squared, which is u squared, times r double prime over r squared, otherwise known as r double prime times u squared. So that's minus u double prime plus 2u prime squared over u minus 2 times r prime squared over r cubed, which is r prime squared times u cubed. So that is minus 2 times u prime squared times u. Over u, I'm sorry. No, times u. No, over u. Right? Because it was minus 2 r prime squared over r cubed. R prime is minus u over u squared, so r prime squared is minus u prime squared over u to the fourth times u cubed, so that's over u. Okay. Well, that's not bad. So that's L over mu squared times minus u squared u double prime. And that is the thing which, by the equations of motion, is equal to minus k over r squared plus L squared over mu times r cubed. Sorry, there's a 1 over mu. So if I wrote mu times r double prime here, then I would get L squared. Let's just write it as L squared over mu and L minus L squared over mu. Okay. Everyone with me? So the equation of motion says that mu r double dot is minus k over r squared plus L squared over mu times r cubed, or minus k u squared plus L squared over mu u cubed. Okay, so this is equal to that. That's the equation of motion using these two tricks. So let's multiply everything by mu over L squared and divide everything by u squared. And what does that look like? Well, let me just rewrite it. So we have minus L squared over mu u squared u double prime is equal to minus k u squared plus L squared over mu u cubed. Or L squared over mu times u double prime plus u is equal to minus k is equal to minus k. Or let me rewrite this as u double prime plus u is equal to mu. Got a minus sign somewhere. Yeah, sorry. I moved it to the other side of the equation, so there's a plus k there. Is equal to mu times k over L squared. Let's put a box around that guy too. This is the equation of motion of a simple harmonic oscillator with a driving force. U is the position of a simple harmonic oscillator. U double prime plus U is the left-hand side of the equation of motion of a simple harmonic oscillator. And the constant term, mu k over L squared, has the form of a driving force for that simple harmonic oscillator. So, I bet you thought that when I was talking about driven simple harmonic oscillators, that you would never see this again. But you were not so fortunate, because there's a reason why we spent time studying simple harmonic oscillators with driving forces, which is that they show up everywhere. And this is the first example. It turns out that the equation of motion of the Earth around the Sun is identical to that of a simple harmonic oscillator in the presence of a driving force. So now we can just write down the solutions. So u as a function of phi, remember I'm using phi as my dependent variable here, not t. Well, there's the homogeneous solution to the equation of motion, a cosine phi, plus a particular solution to the equation of motion. Even I can find a particular solution to that equation of motion. It's just u equal to mu k over L squared. Right? No derivatives. It's constant, so u is equal to mu k over L squared. So let's rewrite that as mu k over L squared times 1 plus epsilon cosine phi, just to make everything look a little prettier. Now, u, let's remember, was 1 over r as a function of phi. So this equation is just an equation for r as a function of phi. R of phi. So let me just multiply both sides of this equation by r. So r of phi times 1 plus epsilon cosine phi is equal to L squared over mu times k. And this L squared over mu times k is the only combination of L, mu, and k that is left in this problem. So let me give it a name. I'll call it p. So the two parameters that appear in my solution are epsilon and p. Now, epsilon and p have names. Epsilon is called the eccentricity of the solution, and p, because it is the only dimensionful constant left in the game, is called the scale factor. And this is the equation of motion for two objects that are related by a gravitational attraction. It is the equation of motion for the orbits of the planets around the Sun. So it's perhaps useful to manipulate this just a bit further to write it in a form that will be more familiar to you. Before I do so, are there any questions? So let me write this in a form which looks a little more familiar. So R, or let's write it this way. X and Y are R times cosine phi sine phi. So this equation is R, which is the square root of x squared plus y squared, plus epsilon times r cosine phi, otherwise known as x, is equal to p. So let's move that epsilon x to the other side of the equation of motion and square it, and we get x squared plus y squared is equal to p minus epsilon x squared, which is p squared minus 2 epsilon px plus epsilon squared x squared. Or just rearranging things a little bit, 1 minus epsilon squared x squared minus plus 2 epsilon px plus y squared is equal to p squared. So we have a quadratic expression in x and y is equal to a constant. This, as you probably learned many years ago, is the equation for a conic section. Thus, the orbits of the planets around the Sun, at least in the two-body approximation, are conic sections. So, and of course, which conic section it is depends on those constants of motion, p and epsilon. Questions? So, let's go ahead and match this. Well, what I would like to do is just describe a little bit more about the solutions to this equations of motion. The solutions for the planets are, of course, ellipses, but I would like to do this in a little bit more detail than I have time for in the last 4 minutes of class. So perhaps I'll just stop and continue next time rather than trying to squeeze it into the last 4 minutes. So that leaves us time for questions, if any of you have them. All right, yes?
Given a symmetry, how do you know how many degrees of freedom you get?
Generally speaking, for every symmetry that gives you one constant of motion, so that means that you can integrate the equations of motion once. So, for example, the 3 translational symmetries allow you to integrate the equations of motion 3 times to find 3 constants, the total momentum in the 3 directions. It turns out that rotations lead to 2 constants of motion because you can do a phi rotation and a theta rotation. So that's why we got down to 1 equation. And then at the end of the day, there's 1 equation, you just got to solve it. So yeah. But, there's no guarantee that a problem will have enough symmetry that you can find an explicit solution at the end of the day. But the rule is that for every continuous symmetry, you get 1 constant of motion. So you get to integrate the equations of motion once for free. Good question. Other questions? Any thoughts? Anyone have any thoughts? We've got 2 minutes. I have you for 2 more minutes. Any thoughts you would like to share with us? Any feelings? Does this move you in any way? No? Yes? Yes? Yeah. I use the word effective potential because it is not the case that two-body motion is the same as one-dimensional motion. Because the effective potential that I wrote down depends on the angular momentum. So usually in a classical system, the potential is just an input into the system. It doesn't depend on what your solution to the equation of motion is. But here, I write things in terms so that it looks like a one-dimensional problem with a potential. But for this other way of looking at the problem, that potential depends on the solution to the equation of motion. Do you see what I mean? So that's why I call it an effective potential as opposed to a real potential. So, I should emphasize that let's scroll up and look at this graph of the effective potential. What does this effective potential mean? So at very large distances, the effective potential decreases as you move towards the origin. So that means that you lower your energy by falling towards the center, right? That's the statement that gravitational forces are attractive. The remarkable thing is that the potential is very large at small distances, which means that when you have angular momentum, there is some sort of barrier which is preventing 2 objects from getting close together. So for that reason, this part of the potential is sometimes called the angular momentum barrier. And you can sort of think of a effective or fictitious force associated with that part of the effective potential. You had a name for this fictitious force when you studied mechanics before. You called it the centrifugal force. And it is something that we will return to later on, probably next week, when we study non-inertial coordinate systems. That's a good question. Any other questions? I've kept you long enough. All right. I'll see you on Tuesday. If you didn't get your first problem set back last time, I have a few extra graded ones up here.